page 332, that was the homework from a couple of classes ago. Just keep it and we'll go over it when I'm back in class. What we're going to go over today is making confidence interval for variance and standard deviation. So just this title here, confidence intervals for variance, standard deviation. We've done confidence intervals for mu, and the last section was confidence intervals for population proportions, or the percents. Key concepts, point of estimates. The point of estimates, same idea. Remember, population variance is sigma squared. Population standard deviation is sigma. We're going to use the chi-squared distribution. One of the charts that you have there is a chi-squared chart. We'll talk about it. Building and interpreting these confidence intervals. So for this, same idea. We're going to use s squared to build our intervals, and for standard deviation, we're going to use s. So we're using s squared and s as our point of estimates to estimate what we think would occur in the population for variance and standard deviation. What use this for? Use it to find out how much a population varies. And when we're talking about population, it doesn't have to be population of people, population of anything. Like my example here, a company makes parts for a car, we'll call it a boozle. The company would like all the boozles to come out exactly the same. Well, that's not very likely. And if they aren't exactly the same, it causes a problem. So if you're making this boozle for a car, you want it to fit exactly right. Otherwise, it causes a problem for the car or for the parts. And if you've ever bought a part from AutoZone or something and it doesn't fit completely right on your car, this may be why. You know, they didn't have their standards up to what they should have been, or the part didn't come out quite right. So we want to see how these vary, how these parts vary, what the variance is, and what the standard deviation is, and then decide whether that's acceptable or not. So how do we estimate the population variance of the population standard deviation using sample data? The variation we see in the sample will be our best guess. So we're going to look at how much the stuff in the sample varies, and then use that as our best guess. Remember, the sample variance is s squared, and we use that as our point of estimate for the chi-squared of the population. And then the sample standard deviation is s, and we use that as our point of estimate for the standard deviation of the population, the sigma. I think I said chi a second ago, I meant sigma squared. To build a confidence interval, we start with the sampling distribution of a modified version of the s squared. So we're using the variance to build our confidence intervals. Chi-squared. This is like a fancy X, and it's chi, K-I. So chi-squared, or chi-squared is what we're going to use for a lot of this. If we find all possible samples of size n, so if we did it for all possible samples, which we can't really do, but we're saying if we could, from a normal population where the population is the big N, the capital N, remember that's the number in the whole population, and then record the value. It comes out using this formula for each sample. So to find our chi-squared, we use this formula, n-1. That's like your degrees of freedom. This is your variance for your sample. This is the variance for the population. And this works for anything where n is larger than 1. So we don't have to take a real big sample. This works for n. All of these chi-squared graphs, they're going to look a little different than the other graphs. Instead of looking like the normal curve, where it looks something like that, the chi-squared is always has a tail out to the right. And we'll talk more about that as we go. Again, main thing here, this formula. Again, our chi-squared graph always, it's got a tail to the right there. That's what it's going to look like. Chi-squared graphs are, and I'm not sure these are extra crap that's just got put on this slide that I can't get rid of. Chi-squared graphs are a family of graphs just like the last ones we did. So the smaller your n is, the more it's like straight up and down here. The larger your n is, the larger your sample is, the more it gets spread out. So properties of the chi-square distribution. Your chi-squared is always going to be greater than or equal to 0. It never goes below 0. A chi-squared curve is a family of curves like I was just talking about. And the smaller the n, then the graph's going to look more like this. The larger the n, then the graph's going to look more spread out. The area under any of these graphs is still always 1, so this area underneath here is 1 or 100%, 1 whole. And it's always positively skewed or skewed right, is what we called it earlier in the year. So that's the properties of a chi-square graph or chi-square distribution. With chi-square, you always have 2 critical values. So we're going to be looking at something that says like 95%, or C, our confidence interval is going to be 95%. Well, we want 95% of the data to fall in here. So we want 95% of the area to be in here. So we need a critical value on the left end, a critical value on the right end. And that's what these stand for. So this is chi-square, and then it's got a subscript L, and chi-square, and it's got a subscript R for your left and your right critical values. Well, if there's 95% of the data falls in here, then that means 5% falls outside. And what we have to do to find these two, we've done this in the past, is we have to take that 5% and divide it in half. So you're getting 2.5% out here and 2.5% out here. And those are the critical values you're going to look for. So to find your chi-critical values, first you got to find your degrees of freedom. So it's just n-1. We've done that. Find the area to the right. On the chart that you have, it deals with area to the right. All the other charts that we've ever dealt with is for our standard normal and stuff, if we were looking at an area, we were always talking about the area to the left of that certain critical value. Well, for the chi-square, it's area to the right. And to find those two areas, you do two things. You got 1 minus C, so 1 minus your like 95% or whatever, divided by 2. That's going to give you this area over here. And then we do this 1 plus C divided by 2, because now that's going to give us this critical value and tell us the area to the right of it, which is going to be a larger number. So we use those two formulas to help us find the right critical value. We use this one. To help us find the left critical value, we use that one. Give you a second so that you can copy that down. Those two formulas, make sure you got them. Then you're going to use the chart this is supposed to be right there, and this is supposed to be right there. I can't get them to move on my PowerPoint anymore. So you use the chart, find your DF, N minus 1, and the two areas to help you find the critical value. If you're looking at, so if you get out your chart packet, and I gotta find mine. On your chart packet, if we look back, we just got done using the T distribution stuff. Well, the chi-square chart is on the back of that page. So if you find your T distribution, it's on the back of that page for your chi-square. So we're going to use that chart to figure out our critical values, our right critical value and our left critical value for chi-square. So again, this is what we talked about. Your confidence percentage is in the middle here. If it's 90, 95, whatever, 99, whatever it is. And then these edges, you're splitting up whatever's left over, and half goes on one side and half goes on the other. An example to find the critical values, your chi-square right and your chi-square left for a 95% confidence interval when the sample size is 18. So the first thing we do, we take 18 minus 1, that's our degrees of freedom. We get 17. Not sure why this doesn't have motion on it. So our DF is 17. We want to find the two areas. So we got to use those two little formulas to find the two areas. So we're going to do 1 minus, or 95%, so 1 minus 0.95 divided by 2, which is going to give us 0.025. And after a while, you'll start to see that, all right, the other one's 1 plus 0.95 divided by 2, which is 0.975. After a while, you'll see that these two just have to add up to one whole. And that'll help you find it so that maybe you don't have to do both of them completely. But we're going to use this and these two to find our critical values. So we go to the chart. So have out your chart, you go down the side of the chart, you go down to 17, and for the first one here, we go over to 0.025, and we match it up, and it says 30.191, and these numbers are going to be a lot different than the numbers that we're used to dealing with. So that's our right critical value. Then we do the same thing for the left one. We go down to 17 and we go over to 0.975, which is 7.564. And those are our two critical values. So if we're looking at our graph looks something like this. One critical value is going to be over here, one's over here. Notice the smaller one always has to go over here, 7.564. And then the bigger one over here, 30.191. So we're saying that 95% is in here between those two critical values. So you have to use a chart. There's no easy way to do this. Doing these confidence intervals, I don't believe there's any way to do them on the calculator, so we have to do them out longhand. How do we build a confidence interval? We start with this. We're actually going to use this right here. This is going to be our formula. That's our confidence interval. Give you a second to write that down. Notice it sort of switches stuff up. You got to remember this. This is your right critical value. It's actually on the left in the formula, and this is your left critical value, and it's actually on the right in the formula. So just be careful of that. Make sure you're dividing the correct way. The reason for that is if you're dividing by the right critical value, that's going to be a bigger number, so it's going to end up giving you a smaller number over here on this side and a bigger number on this side for your interval. This is the formula that we want to use, not this one. We're not worried about that. That's what we're starting with, but it's just been mathematically moved around to make it so that we can find our confidence interval. And this is the confidence interval for the variance. So we're going to say we're 95% or whatever the C is, confident that our variance falls in that interval. Just like the other things, I think what's going to be on the next slide, just like when we dealt with variance at the start of the year, variance was always sigma squared, all right, and then to find the standard deviation, you just took the square root of that, and that's what we're going to do with these. We're going to find these two answers. And if we want the interval for the standard deviation, then we just take the square root of both sides. And that's what this is. That's what this formula is. So this is for your standard deviation. This you already have down. So all we're really looking at here is for standard deviation. You just take your two answers on each side. Actually, you're taking the square root of the middle term there too, but standard deviation, you just take the square root of those two, and now in the middle here, you're left with just sigma instead of sigma squared. Again, these can't really do them, you can't do them on the calculator as far as just punching numbers in and getting out what you want. It's gotta be done out longhand, so you gotta be careful as you're punching this stuff into your calculator. Give you a second to copy down that formula, make sure you got it down. So making a confidence interval, things you gotta do, or things you gotta have. First of all, it's gotta be normal. They're gonna tell you that. Number two, you gotta find your N and your DF, your degrees of freedom. Number three, find your variance of the sample, which we could do using this formula. They're probably gonna give you this each time. Then you're going to find the critical values. You're going to use the chart for that, and not only the chart, but to use the chart, you got to have your degrees of freedom, and you also have to have your two areas. And remember, your areas are the little formulas: 1 minus c divided by 2, and 1 plus c divided by 2. Then you're just going to take all that information and plug in to each of these two. Notice that the tops on both of these are the same. And you're just dividing by the right critical value that you got from the chart and the left critical value that you got from the chart. Take the square root of both sides. If we just wanted the variance, then we stop here. If we want to go on and do the standard deviation, then we got to take the square root of both sides to find that interval. The other thing, some of the problems on the homework, you're going to have to punch the list of numbers, or punch their numbers into a list on your calculator. And if you do that, then you're going to use, from that, you're going to use the S. And you're going to have to square it to stick it into the formulas. So if they don't give you S, then you're going to have to punch the list of numbers they give you into your calculator on the list and do the one variable stuff that we did at the start of the year to find the mean, standard deviation, all that stuff. And then you use that S to put in here. You randomly select and weigh 30 samples of allergy medicine. The sample sigma is 1.2. I'm not sure, that shouldn't be a sigma there. That should actually be an S there, because if it's a sample. Assuming the weights are normally distributed, construct a 99% confidence interval for the population variance and standard deviation. So the first thing we do, we find N, which was 30. DF then is just 30 minus 1, which is 29. Our C is 0.99. They told us that. find S, which they told us, 1.2. Make sure you square that S, because that's what we're going to need in the formula. So S squared, 1.2 squared is 1.44. That's what we're going to plug into the formula. Then we're going to find our critical values. To find our critical values, we have to use our chart, but first we know the DF, and we gotta find the areas. So we do 1 minus our C, which is 0.99 divided by 2, that gives us 0.005, and then 1 plus 0.99 divided by 2 is that. Switched on me. Then we grab our chart, and on our chart, we use the DF and this number to find our right critical value, and we use the DF and this number to find our left critical values. If you go on the chart, hopefully you see that the right critical value is that, left critical value is this. So that means our graph looks something like this. Our right critical value over here is 52.336. And our left critical value is 13.121, and we're 99, so there's 99% of the data in the middle here, and then the two other parts are split up, half on one side, half on the other. So half of a percent over here, half of a percent over there. Once we have our two critical values, we know our S and we know our S squared. Next thing we're going to do is plug into this formula. So N minus 1 is 30 minus 1, which we know is 29. We've already done that. Our S squared was 1.44, so we're plugging that in there. And we put in our critical value. Remember, our right critical value goes on the left side when we're plugging in to do the interval. So this is the right one. And our left critical value goes on the right side. Sort of backwards. We do all the math. That's our interval for our sigma squared. So we're saying we're 99% confident that the variance falls between 0.80 and 3.18. And then if we want to do the standard deviation, this one's the standard deviation interval, then we take the square root of both those and we say, then we can get our interval, which is this, and we say that we're 99% confident that the standard deviation is between 0.89 and 1.78. Nothing real hard, just got to be careful, easy to make a mistake. The assignment's on page 341, problems 3 through 8, 11 through 15, 17, 19, and 24.